let's talk about Pascal's principle. So hydraulic lifts, if we exert a pressure um, on a panel containing a fluid, it will be transmitted undiminished through the fluid, acting in all directions. So pressure on one side can be matched by the pressure on the other side based on the walls, the container. It can be transmitted. So if I push down with a force on a small panel, I could lift up something like a heavy car. And how does that work? Well, energy must be conserved. So the work done, because I push down on this panel with a force that moves a distance, will push this up, the car, with a more force because it's got a larger area. The pressure remains the same, and that's what's communicated. But the distance that it has to travel will be way less because the volume of the change of me pushing this down will be not as much in terms of height on the large panel. This means that energy must be conserved and the work done in lifting must equal the work during compression. So our mechanical advantage, or the reason why this all is very helpful, is that our force output 2 divided by force 1 will be the ratio of the areas, area 2 over area 1. A small distance must be pushed down a large distance for the large piston to go up just a small distance. And again, we're talking about force times a distance will equal force times distance. Okay. So let's look at a couple samples. A large piston on a hydraulic lift has a radius of 20 centimeters. What force must be applied to a small piston, radius of 2 centimeters, to raise a car, a mass of 1,500 kilograms? So, well, we start with our pressure 1 equaling pressure 2, which means force 1 divided by area 1 equals force 2 divided by area 2. Well, we're looking for what force must be applied, or the first force we talked about, right? Because we're applying the force over a small area to raise a heavy car, a bigger area. So F1 will equal F2 over A2, and we're going to move the area that was down here up next to it. Well, the car's force is 1,500 times 9.8 because we're working against gravity, and the area is going to be pi times the radius squared, and the other radius is, or the other area is pi times the other radius squared. Now, you could have converted and had moved both these into centimeters, but even if I put a decimal in front of that number and a 0.02 over here, the units would cancel. And what else cancels? That's right, pi cancels. All in all, force 1 equals 147 newtons. That's how hard we must push. So what's our mechanical advantage? Well, mechanical advantage equals force 2 over force 1. And our output, force 2, was the car being lifted up. That's the 1,500 times 9.8. And that's all over 147 newtons. The other way to do this, by the way, that's 100. The other way to do this, and to prove that I can do that real quickly, is because really it's just area 2 over area 1. And we had pi times 20, that's our output, squared, over pi 2 squared. And of course our pi's cancel, and we find out that we just need to take 10 squared, or 100. And it's area over area, or it's force over force. So the unit for mechanical advantage is unitless, 100 units, or 100 times the force output. All right, so we have pressure in a tube, and the heavy stuff, mercury, on the left, and the light stuff, which is the oil, and maybe some mercury, still on the right-hand side. And in these tubes, the pressure on the left will equal the pressure on the right. Now, it's always good to think about the absolute pressure, because even though pressure adds, that's our guiding principle, that we have pressure times gravity times height on the left from that little bit of mercury will equal, or at least the difference in mercury, will equal the atmospheric pressure plus rho g h. Now, of course, this is the rho from the left side, which is the mercury, and the height of the left side. And this is the rho of the oil. I shouldn't use 0, though. I should use, let's just say the right side, because it's the height of the right side. So I have rho of the mercury times the height of the left side divided by the height difference of the right side. And that should give me, oh, you're like, wait. We skipped a step. Subtract that out, cancel out the gravities. That should give us our density of the right-hand side. So I have rho h of the left side divided by the height of the right side will give me the rho of the right side. Then we just plug it in. 13,600 times 3.5 over 57.3. That's the heights. And we get 830.7 kilograms per meter cubed. A fluid will exert pressure in all directions. A fluid will exert a pressure perpendicular to a surface it contacts. And pressure is affected only by depth, not shape.